So Jan would give his final lecture today. It's wonderful.
Perfect timing. All right. Thanks very much and welcome back again. And congratulations for making it all the way to the end, to the final lecture, at least my final lecture today. So today really will be essentially a collection of remarks and bits and bobs, odds and ends that are very good to know, especially in the context of doing or applying methods like Chaboty or quadratic Chaboty to the examples of modular curves. And so we'll explore a little bit more the analytic side of things in the Birchon-Swinnerton-Dyer conjecture that we started off with in the very first lecture. And just to summarize the point where we're at, I promised you in the very first lecture that we were going to study the arithmetic of elliptic curves over Q, and also more generally, maybe abelian varieties defined over Q, by looking at collections of special points on the modular curves, and specifically the modular curves x naught of n will play a very central role in these lectures. So that's really the primary example that we will focus on, and the reason being that elliptic curves over Q always admit a finite map from this modular curve x naught of n, where n can be taken to be the conductor of this elliptic curve E. And so we saw that constructing special points on this modular curve that have certain fields of definition that are finite extensions of Q will give us likewise such points on the elliptic curve E over Q. And of course, in the Birchon-Swinnerton-Dyer conjecture, one of the crucial difficulties is to construct systematically sets of rational points on them. Now, we mainly focused so far on the first source of special points, which was coming from the cusps. We learned how to calculate them, and we saw that they always define algebraic points on these modular curves. Very often, they're actually rational points on these modular curves, but at worst, they're defined over a cyclotomic field. Now, we saw that in the Jacobian of the modular curve, we can at most get torsion points by Mann and Drinfeld. And so in this modular parameterization, that's a little bit disappointing because if we map them through, of course, we're going to get torsion points on the elliptic curve as well, whereas the difficulty in Birchon-Swinnerton-Dyer is, of course, mainly constructing rank. Nonetheless, the structure of this torsion was very interesting, and that's really what Barry Mazur exploited. So he looked at consequences for the torsion subgroups of elliptic curves, not using this map necessarily, but maybe more a map to the universal elliptic curve that lives over this modular curve. So we've been studying really, if we had an elliptic curve, and here maybe I should draw also 2 points on each one. One being the origin, the other being, well, maybe not a point, but a subgroup. Anyway, so it's only a picture. It's a modular curve that parameterizes certain things. Namely, in this case, it parameterizes elliptic curves together with a cyclic subgroup of order n that is defined over the base field. And so we saw actually that by considering a diagram like this and by coming at it in this direction, Barry Mazur was able to use the torsion in the Jacobian generated by these special cusps to do a cuspidal descent, what one might call a cuspidal descent, so a descent with respect to primes that divides the order of the torsion that's generated by the cusps. Not on the full Jacobian J naught of n, but rather on a piece of it. And he identified the so-called Eisenstein quotient, which is where this descent works out beautifully, and where he can show his famous torsion theorem that we had on the board right at the end of the previous lecture. Okay. Today, we're going to focus on the second source of special points that we have in modular curves, namely the points of complex multiplication. So we're going to study, or at least make some remarks, the points with complex multiplication, which corresponds to elliptic curves that have extra endomorphisms, which is what I try to capture here with this tiny end that probably no one can see because it's too close to the light. But these blue elliptic curves here on the picture, they have additional endomorphisms. So we're going to study CM points, and we'll focus on x naught of n. And one of the things we're going to do is to find an alternative to Mazur's Eisenstein quotient that also satisfies the properties that we had up on the board right at the end. Namely, it's a quotient that's going to be of rank 0, and we're going to prove that it's of rank 0 in a very different way today, and it's still a formal immersion at infinity. So we will find an alternative quotient called the winding quotient. And to do that, we will have to have a brief discussion of the work of Gros and Zagier, as well as the work of Kolyvagin. Of course, I only have one lecture, so these will be brief comments, but let's frame them in our story as it stands now, and let's see what the consequences are also for these torsion questions that we've been studying so far. Okay, so a bit of CM theory. So for the most part, I'm going to assume, in the lecture at least, that people are familiar with the theory of complex multiplication, but because that might not be the case, I also wrote quite a bit of it about complex multiplication in the notes. And so the starting point really historically for the theory of complex multiplication was a study that happened mostly in Germany in the late 19th century of special values of certain transcendental functions like the J function. The J function I'm just going to define as a formal Q series for you. So this is a Q series that, well, I'll work out in a second, where I'm using the variable here Q to mean the exponential of 2 pi I tau, where tau is contained in the Poincare upper half plane, for which I'll use this fancy German H, and it consists of all of the complex numbers that have positive imaginary part. Okay, so if you work this out, you find a very nice Q series, and one interesting thing to note about it is that it's integral. Meaning all of its Fourier coefficients, which I can only remember a few, are actually integers. So this is worth noting, is a power series in Q inverse ZQ. I can view it as a holomorphic function on the upper half plane through this variable transformation into tau that I've written down here. It's holomorphic on the upper half plane, and it has a simple pole at the cusp infinity. It's SL2Z invariant, yeah, so it's looks like a modular form of weight 0, but because it has a simple pole, it's only a weakly holomorphic modular form. And it's essentially the unique such thing that's SL2Z invariant in the sense that everything else is a rational function in this one. Okay, so my sentence here starting point is a study of special values of this J function, and now I have to tell you where I'm going to take these special values. I'm going to take these special values at arguments tau in the upper half plane. They're very special. They lie in an imaginary quadratic extension. Quadratic. Meaning they're complex numbers, but they satisfy a quadratic polynomial with negative discriminant with integer coefficients. Now these things, these special values are called singular moduli. And you can find tons of examples in the notes if you want to see some explicit numbers, but I'll spare you those, and also spare myself from having to write them all down on the board. But they're really beautiful objects, and if you stare at them, you see a lot of rich arithmetic encoded in them. And that's one of the things that we're going to study now. So I want to make a definition. I want to say O, curly O, is my notation for the order associated to this imaginary quadratic tau. And it's defined to be the set of all the complex numbers that map the lattice Z plus Z tau into itself. That's what the associated order is. So it's all of the complex numbers such that if I take this lattice Z plus Z tau, there's a lattice in a quadratic imaginary field even, and I multiply them by Z, I land still inside of that same lattice. The associated order to this tau is what I'll call it. Okay, now here's a theorem, and the proof of it you can find in full in the notes. It's a classical theorem, which says, and probably most of you have seen it, that the singular modulus j of tau, so the special value of this j function at this imaginary quadratic tau that I've chosen, is algebraic. And not just that, it's an algebraic integer. Already quite striking. And it generates the ring class field Ko over K. So this means if you join this value to K, you actually generate the ring class field. Now the ring class field, I remind you, Ko is a ring class field, which means that through class field theory, it's the extension associated to a very specific quotient of the Adel class group. It's the quotient that we take when we take the finite Adels in K. We quotient out on the left by the global elements K star. And I quotient out on the right or on the left, doesn't matter, but I prefer to do it this way, by the profinite completion of O and the units in there. So just to remind you, so here, profinite completion of O, this comes out to be O tensor ZL for all primes L, and K hat similarly, this O hat, extend scalar. So these are the finite Adels, and then I take the unit group in them. And class field theory gives you actually for every finite index open subgroup that you take of that Adel class group, gives you a corresponding quotient. This is called the Artin map. It's an isomorphism with the Galois group of some finite abelian extension of K. And that's the abelian extension that I've called Ko. Okay. So this Adelic description here is just, by definition, essentially, the Picard group of O, which can be described globally as the set of non-zero invertible fractional ideals for O, modulo the principal ones. And so when O is a maximal order in K, this is just a class group of the number field K, but pay attention, O does not necessarily have to be a maximal order inside of the imaginary quadratic field, that is its field of fractions. I didn't say that, but field of fractions of this is what I've called K here. Yeah. So it could also be a non-maximal order, and as the index of non-maximality grows, this Picard group grows and grows and grows, and this extension sees more and more and more of the class field theory of the imaginary quadratic field K. Okay. All right, so this is part one of the theorem, I guess. The fact that it generates this ring class field is part one, and this bit below here is just a definition of Ko. There's a second part also, which tells us exactly how these algebraic integers relate to each other. In fact, if I change tau to a different tau, which has the same associated right order, which means that the ideals that I've written down here, the Z plus Z tau, correspond to different ideals, I guess, inside of O. If they have the same associated right order, then in fact, these things are conjugates to each other. They're algebraic conjugates of each other. So this is part two of the theorem, if you like. So furthermore, for A and B invertible ideals of O, I can make a small abuse of notation. So this will correspond to some Z plus Z tau A up to homotopy. And likewise, this one will be Z plus z tau b. And instead of writing j of tau a or j of tau b, I'm just going to write j of a or j of b, yeah, just to keep it notationally as simple as possible. Yeah? We have the following relations. So we have that if I take the j invariant of the product of these two ideals, then actually that's the same as if I would have taken the j invariant just of the first one, and I would act on it by the element of the Galois group of this extension, which I know contains all of these invariants. That is the inverse of the element corresponding to B. Yeah? So B, my ideal, defines a class in the Picard group. It's an invertible ideal. I trace it all the way through, I invert it, and then I make it act on J of this equality. Likewise, it is true that if I take J of A, and I complex conjugate it, yeah, that's the action not just of this Galois group, but also of the Galois group of K over Q, then I obtain J of the inverse ideal. The complex conjugate ideal. It's really the same thing. All right, so these singular moduli, the proof of these facts you can find in the notes, and in fact, I try to do it in the most classical language, which I think is a very nice way of proving these kinds of theorems. It's not the full scope of the theory of complex multiplication, but it's pretty close. In fact, the arguments that are in the notes, if you elaborate a little bit further on them, you also get the algebraicity of the x-coordinates of the torsion points on elliptic curves with complex multiplication, if you try and phrase it more geometrically. And that gets you pretty close, actually, to the statement that I'm about to give, which is the fully general statement of the theory of complex multiplication that is the most flexible and powerful. So these statements can be bootstrapped up to statements that sort of contain all of the theory of complex multiplication, or at least the reciprocity laws, into one picture, which I want to draw for you. So I'll just say here that the proof is in the notes. And what we'll be, so I'll skip it in the lecture. And what we'll be mostly concerned with is a sort of geometric reinterpretation of this whole picture. And an interpretation that allows us to use the observation that this j function is really just a coordinate on x of 1, the modular curve of level 1. Uniformize it, it gives you an isomorphism with P1 explicitly. So what we're saying here is that in the model, the integral model, which has function field Q of j, the coordinates of these CM points are algebraic, and they kind of relate to each other in this way. There are finitely many of these invariants, and they're all related to each other. So the generalization, I'll say, rests on the fact, or on the observation rather, that the j function is really a uniformizer on x of 1. So it gives you an isomorphism between the modular curve of level 1 and P1, yeah, over Q, if you want. And in general, for other modular curves, we can use the formulation of Shimura to phrase this kind of theorem in a very succinct way that's excellently suited to computations. They formulated what's often called the main theorem. It's not the only theorem in complex multiplication, but it's often called the main one for general modular curves. And that's what I want to tell you about next. So the formulation, as you may have guessed, will be an adelic one. As we've already seen a little bit come forward in the statement of this theorem, we'll now phrase everything adelically, including the uniformization of the modular curves by the upper half plane. We'll see an adelic version of that. And I'd like to begin by taking our CM point, tau in H, with complex multiplication, so meaning the associated order, which I'll call O, is an order in an imaginary quadratic field. So call it O sub tau. If you want to write it down explicitly, it's actually given by the following lattice, so Z plus Z times A times tau, where A is the first coefficient of the quadratic equation that is satisfied by tau. So where A tau squared plus B tau plus C is equal to 0, all of A, B, and C are in Z, and they have greatest common divisor 1. Yeah. And that gives a well-defined notion of this O tau. In fact, you can see that this must be inside of the order. Yeah? If I multiply tau by this, I get A tau squared, which is minus B tau minus C, which is again the original. Spanned by tau. And the converse is also easy to obtain. So that's an explicit form of what this order really looks like, which will be useful in this sequence. Okay, so associated to this point, there is uniquely an embedding and it's going to be an embedding of K in the matrix algebra M2Q. I'll give it a name, I'll call it eta sub tau. And it's going to take my elements in K, it's going to turn them into matrices with rational entries. And this embedding is uniquely characterized by the fact that if I take eta tau and I evaluate it on some element alpha in K, I get a matrix, and this matrix I multiply by the column vector tau 1. Yeah? So now I get another column vector, and I want these entries to be alpha tau alpha. Yeah? So essentially I want multiplication by alpha here that gives me some base change, I guess, in this lattice, Q rational base change, and I want that base change to be given by this eta tau alpha. So it encodes the action of K on this order. Okay, now explicitly, to make it a little less mystifying, if I have some general element in K, which I can write always in this form, x plus a tau y, and I'm going to take out the a just for notational convenience, but everything is certainly something in Q, and then something else in Q times a tau. Everything in K can be expressed in this way, and what that gets sent to is something really rather explicit. The x's, well, the x's are just going to be diagonal matrices. Yeah? So that's just multiplication by a scalar in Q. So the x's had better arise. Maybe I make this matrix a little bit bigger for the people sitting near the back. So I get x and x. And then the y's, to figure out the y's, try this for yourself. It's a very elementary exercise to see that the numbers you get in this embedding are precisely minus by here, minus cy there, and ay down there. So that's explicitly where an element of K gets sent to. Okay, so this will be an identity that we'll use a couple of times in this sequel. All right, so we're still on the upper half plane. We haven't really done much with modular curves. I've just associated this mysterious embedding to a CM point in the upper half plane. What am I going to do with this embedding? Well, now I'm going to take any compact open U inside GL2 Z hat, where Z hat, just as before, is the profinite completion of Z. It's just the product of all of these ZLs, where L runs over all of the primes. I'm going to take a compact open subgroup of GL2 Z hat. And associated to this data, I can make the following commutative diagram. I can take the upper half plane, but for this picture, actually, I also want the lower half plane. I'm going to denote that by H plus or minus, which means essentially C minus R. Yeah? So maybe I'll write this in a different color so it doesn't distract too much from the diagram. That's the upper and lower half planes. Okay. I'm going to take the product of this with GL2 Q hat, a very large group of the finite adels of Q. And on the left, I'm going to quotient out by GL2Q, and on the right, by my compact open U. Okay, very strange double coset space. The first thing I have to tell you is how everything acts. So GL2Q acts by linear fractional transformations or Möbius transformations on H plus minus, and just by left multiplication on this group. So the natural things that you would expect. U just acts trivially on this first copy, and it acts by right multiplication on the right. Yeah? Okay. All right, so mysterious double coset. The reason for considering this is that this is precisely the adelic interpretation of the modular curve, or at least the affine part of it, associated to this compact open subgroup. So for any congruent subgroup, there will be some associated compact open subgroup of GL2Z hat. Yeah? And the complex points of the associated affine modular curve, YUC, are canonically identified with this double quotient. So if you don't take this, you get the infinite tower of all of these curves, and that's really where Shimura phrases his reciprocity law. But we'll do it on the finite quotients only. Okay. All right, so why is this interesting? Well, because from this data that I have here on this board, I also get embeddings of K star and its adelization inside of this space by just putting everything into the second factor. I get associated to the left board here, the profinite completion of K, units modulo K star, and I get a map like so. And that map is given by sending an element alpha, I guess, or well, I'll write it here. So what I'm going to send it to is an element of this double coset space. I'm just going to tell you a representative for it before I quotient out. So I have to give you an element of the upper half plane and something in GL2Q hat. Well, there's only one thing to guess, really. What's going to be the element of the upper half plane I'm going to send it to? Well, tau. And the element of GL2Q hat that I'm going to send it to is going to be the adelization of this map, eta tau. And to distinguish it from this global one, I just take all of the local ones together, evaluated at some argument, where the argument now lives inside of there. Okay. Already checking that this is well defined, so modulo K star is very instructive to do. And this gives us a well-defined map from this quotient, and this quotient, of course, we recognize. Yeah, that's before we quotient out by anything. That's the Adel class group of this imaginary quadratic field. So via the Artin map, I also get an identification here of the left-hand side, and I'll erase this in a little bit more space. With the Galois group of the maximal abelian extension of K over K. Yeah. Now this identification I can make via the Artin map, as I did there, but to already preemptively make my arrows commute and not anti-commute, I'm going to take the inverse instead, because I know this theorem and I know there's going to be some inverse twist. So this identification here will be made by the inverse of the Artin map. Yeah. Okay, so this whole yoga gives me a map from here to here. Okay. All right, now what can we say about this map? First of all, the image of this map in this generality, so I didn't commit to any specific choice of U or anything like that, is always going to consist of algebraic points. Now, the coordinates of these points are always going to be algebraic. Of course, there's already a little bit of fine print, right? Because I have the C points here of a variety, but what kind of model do I take for this thing? What set of equations do I take to express this modular curve? I'll take the so-called canonical model. Yeah, this is the general one, which for the special case of x of 1 is really just the one that has function field q adjoined j. But in general, there's a notion of a canonical model. And in fact, I've been implicitly using that the whole time already throughout these lectures. So there's a canonical model of this guy. And in this canonical model, the image of this map is always going to be algebraic. So the theorem, in fact, am I going to state this theorem? But I still want to do that. Because the theorem is that this map, which I haven't given a name, but I might as well call it psi. Oh, no, that's an ugly psi. Let's call it epsilon. Always seems fancier when you put an epsilon. There we go. So this map epsilon is always algebraic with respect to the canonical model and defined over the maximal abelian extension over K. And, wouldn't you know it, it's Galois equivariant. And this is the way that Shimura thinks of the reciprocity law. And you see, it's a little bit more mysterious. It's further away from this classical way that we like to think about things so far. We have to describe everything adelically. And the price we pay is that for any given concrete situation, we have to do a fair amount of unpacking. Yeah? We have to see what the consequences of this theorem are in the specific case that we're looking at. But the huge advantage that we get is that it's so general and it's such a clean statement. So this is really what, in practice, is going to be very useful. Okay, so maybe one case, before I talk about Heegner points, which will be a kind of slightly more special case. Let's just set U to be equal to the maximal compact open. Being just the whole group itself. When U is equal to all of GL2Z hat, yeah. Well, yeah, and what we get here is really the quotient. You can work this out, it's a great exercise actually to do, is if you work out this quotient, you have to use strong approximation on GL2Q hat. And if you do that, you see that you just identified this modular curve here with the quotient of H, just one copy of H, by SL2Z, or two copies by GL2Z, as you wish. And so what we get back for this specific case is an old friend, namely YU is just Y of 1. Yeah, it's the affine part of the modular curve Y of 1. And I've already told you that the canonical model here will be generated by this J. So saying that this point, the coordinates of this point are algebraic is the same as saying that the J values of these things are algebraic. Yeah? So you can unpack it. Moreover, the Galois equivariance will translate precisely into this reciprocity law that I have up here by the Artin map. So it's a really instructive exercise to do this, just to get used to the language and to learn the kind of tricks that you need to unpack it. It's like 2 or 3 tricks that you need, and once you master those, you can really do a lot of calculations, determining the fields of definition and the reciprocity laws of CM points on them. Yeah? So note in particular, I haven't really assumed much about U, so we'll only see congruent subgroups, that's a fact of life, but I haven't assumed anything else about U. And I also really haven't assumed anything about tau. There's no Heegner hypothesis yet or anything. So it's very, very general when set up in this way. Okay, so that's this case. So I'll leave that also for you to check, and you can find the details of it in the notes if you need help unpacking the definition. Now, I would like to take a slightly more general situation rather than just the full GL2Z hat. I'm going to take the following. I'm going to take U to be the thing corresponding to gamma 0 of n. What's that going to be? It's going to consist of all matrices A, B, C, D, which are now all elements of Z hat. Yeah? It's an element of GL2 with coefficients in Z hat. Maybe I'll write that. And this C, this element of Z hat, when I take it in the quotient Z mod NZ, or Z hat mod NZ, it's just going to map to 0. Mod, I guess I used a capital or lowercase n. I'll just use a capital. I think that's what I did before in this lecture. Now, in this case, by a very similar argument to one I skipped before, the quotient will be y0 of n. So the affine part of the modular curve y0 of modular curve x0 of n, whose picture is up on the board all the way on the left. And this will be the primary case of interest. We get in this case the modular curve y0 of n, whose canonical model is defined over Q. In general, if you take some general U, you have to be a little bit careful. The field of definition is determined by the determinant of the elements in U and what they span. So you can find this in the notes also. The set of, the field of definition and the set of connected components will be determined by that. So this one will be defined over Q in its canonical model. And what we're going to do now is we're going to look back at our explicit form of our embedding. Because you see, what we would like is that if we map a point tau, we'll be able to say something about the kernel of this action. We'll hopefully be able to say something about which compact open subgroup of the Adele class group of K will act trivially on the image. That would be very nice if we could do that. Yeah? So in other words, if we translate by something in it, we still map to the same point because we translate likewise by something in U. And in fact, this is very transparent now if you look at this explicit expression that we have up here. See? Because what I want is for this explicit expression, if I have an element of O, or more generally, if I take the adelic version with a hat on top of everything, the element of O hat, I would like this kind of thing to land inside of U. And my definition of U is that the lower left entry should be divisible by n, this integer that I've picked. And so we see that if we take O, we're always going to land in Z hat. That's what proved the theorem in the first place for level 1. But on this level n case, that's not necessarily going to be true. That's only going to be true if A is divisible by n. That's the only case in which we'll act trivially by O hat star on the right here in this Galois equivariant map. So this kind of consideration, I'll write this down, shows to us that the CM points for which the first coefficient A is divisible by n play a very special role. They're defined over a much smaller abelian extension than all of the others. And that's what we call the Heegner points. So suppose that tau is in the upper half plane and satisfies the condition that n divides this first coefficient A. Yeah? And that's a well-defined condition, right? Because I guess, what did I write down? I said A, B, C have to be in Z and their greatest common divisor has to be 1. That pretty much pins it down up to plus or minus 1. So this condition is uniquely determined. Okay, so suppose that we have that. Now, is that possible? Well, sometimes it's possible and sometimes it's not possible. Because you see, this tau has a certain discriminant. And depending on what that discriminant is, this may or may not be possible. So note that this is only possible when the discriminant of tau, or the discriminant of the quadratic form ABC, which is defined to be b squared minus 4ac, well, if I reduce this modulo any prime that divides n, this term goes away. And I see that the discriminant must be a square modulo that prime. So that gives me for every prime that divides n, some condition on the discriminant, namely that it has to be a square. So modulo every prime e that divides n. Yeah. This condition here, that the discriminant of tau is such that it is a square modulo every prime p divides n, we'll give a shorthand name to that. So this condition, red star, we'll call the Heegner hypothesis. Okay, so star. It's a hypothesis about the discriminant and n. Yeah? So it's two integers and they have to satisfy some sort of compatibility. We'll refer to that as the Heegner hypothesis. Okay. All right, so suppose that we have a tau such that n divides a. Then what can we do? Assume it's possible, we found such a thing. Well, then we can look at this reciprocity law and we immediately, by the argument that I sketched before, find, well, n divides a already. So everything's already going to be, when I map it through, an element of here, so that if I shift by it, I'm actually inside of u, by my definition of u, because the lower left entry is divisible by n. So that means that in the quotient, it's the exact same thing, meaning that O hat star lies in the kernel of this map. Okay. All right, so that implies, in this case, the image of tau on y0n, in other words, the image of 1 under this map through this identification, is defined over the ring class field KO over K. Moreover, the reciprocity, if you unpack it, will also tell you that these points are conjugate to each other under the action of the Picard group. That's a bit a trickier calculation, but you can also do it. Okay. So these points are called Heegner points. And amongst all of the ones of a fixed discriminant that come from something of a fixed discriminant tau, they're the ones with the smallest field of definition, yeah? Just a ring class field. If A was not divisible by n, then we would see that O hat wouldn't be in this kernel, right? And it would only be in this kernel if then Y became divisible by n. So we wouldn't get the full O, we would get some smaller suborder of it. So it would be defined over a larger field. But for Heegner points, this is not necessary. Okay, so I'm going to call the Heegner points the ones that are defined over the ring class field. Sometimes people call the following one the Heegner point. So we can also form P delta, where the discriminant of tau is usually called delta. To be the trace of that point, so I take that point P tau, I didn't give it a name. So the image E tau of tau, that's defined that the coordinates of this thing are in KO over K. Yeah? Now what I can do is I can view this by taking the cusp infinity, for example, as a divisor on the Jacobian. And on the Jacobian, it's still going to be a very nice point defined over KO. Now on the Jacobian, this point is defined over KO. I can consider all of its Galois conjugates. Yeah? So all of the translates by the Picard group of O of this point, and I can add them all up in the Jacobian. And the sum, of course, will be invariant under the action of the Picard group. So if I take the trace from KO down to K of this, and view this via the usual embedding as an element of the Jacobian J naught of n, it's actually going to be K rational. By definition, I've just forced it to be K rational by taking this trace. Okay. All right, so what do these points look like? And we've made this kind of bizarre construction. Let's see that come to life a little bit. On an example. All right, so here's an example. I'm going to take n equal to 58. And I cannot emphasize enough how little thought I put into the choice of this n. You can do it for any n you like. And in fact, I encourage you to do it. It's really instructive to do these kinds of computations. You learn a ton, not just about the Heegner point construction, but also about elliptic curves and modular forms in general. Okay, so what we have now is we have an elliptic curve, E, which I found on LMFDB. It has the following equation: y squared plus xy equals x cubed minus x squared minus x plus 1. Yeah. The conductor of this curve is 58. Yeah. So I know that there's a map from this curve, x naught of 58, onto this elliptic curve E. Yeah. Now, x naught of 58 is quite a large modular curve. It has genus 6. Genus G is equal to 6. And this one, of course, is genus 1. So inside of the Jacobian, this map kills a 5-dimensional piece. Okay, actually, well, okay, maybe I don't have to tell you, but in case you know what this means, this just so happens to be x plus 0 of 58, where plus, that's always an ambiguous notation, but here I mean I've quoted it out by all the Atkin-Lehner involutions. So the one at 2 and the one at 29. But okay, that's just an aside, it's not very important. Okay, now what's true about this elliptic curve is that it has rank 1. You can just believe that, for instance, by running a 2 descent. And as we learned, that's not the kind of thing we like to do by hand. But with the press of a button these days, we get it from magma. And in fact, it tells us more. It tells us also that its Mordell-Weil group over Q is generated by a point, which I'll call little p, where p has the coordinates 0, 1. That's the solution. Maybe you had already found. Okay, so this generates the Mordell-Weil group. It has no torsion. It's just isomorphic to Z. Okay. All right, so the second part of this is, well, we made our Heegner point construction, but we made it on the modular curve y0 of n. So the points a priori will lie on this curve, and then I'm going to map them down onto E and trace them all up. That's the point I actually want to compute, which will be a k rational point where I still haven't chosen my k, right? I have a choice of k that I haven't made yet. I can take any CM point I like with any discriminant, even though I do know I better take care of the Heegner hypothesis. Yeah? Otherwise, there are no such points. Okay. All right, so the first thing we have to do to compute these kinds of points is, well, the theorem tells us that they're going to be algebraic, and we know what they are. They're just, we take tau in the upper half plane, and we map them through to x0 of 58. Yeah? Under the parameterization, that's just taking the quotient by gamma 0 of n. So I'm going to bypass this curve. So there's a, I didn't write this, but there's an h that goes here, which is quotienting out by gamma 0 of 58. The point tau starts here, then it goes here, and then it goes here. I'm never going to compute with this one. That's a bit messy. It's genus 6, etc. I'm just going to go all the way from H to E. Yeah? That's the so-called modular parameterization of E, which was something that people were able to do already mechanically for any given example long before Wiles was proved. So it was never a mystery that this was a modular elliptic curve. You can just write down explicitly the parameterization. So it's uniformized by H. And this uniformization, which is the composite from H to E, I'll use the coordinates or the functions, really, x of tau, y of tau, where x and y are the things that we need to compute to be able to make everything explicit. Yeah? So this will go to the C points, where now our task is to find this x and y. Yeah? So they're functions, really, on the upper half plane that are holomorphic, except at infinity. They're invariant under the action of this group going from here all the way down to here, which is gamma 0 of 58 together with these two Atkin linear involutions, if you want to know what that group is. So that's what x and y satisfy. That doesn't quite uniquely determine them, but then if we also demand that the canonical Tate differential pulls back rather to the associated modular form times dt, you know, d tau with a 2 pi I for good measure, then that pins them down exactly. So let me write that down. We have an x of tau and a y of tau. And we don't know much to begin with. We only know something about their poles because they should be the x and the y coordinate on that. So they're going to start off by something like this, yeah, as a Q expansion. And don't get confused here between the difference between tau and Q. Q is exponential of 2 pi I tau, like before. That's how they start off. Yeah? So there's some more terms to compute. If we, in addition, demand that the pullback of the canonical Tate differential, so which is y plus, so in this case, so A1, I didn't write this down. So it's 2y plus A1 of x, and A1 is 1. Okay, that's good. So that's x. That must be the same as 2 pi I f of tau d tau, where f is associated, the associated modular form. So I didn't write this, but the associated form E. It's in the notes if you want to see explicitly what it is. And I'm going to normalize my f so that the first coefficient is 1. So the usual thing. So this is the system of equations that we're trying to solve. And in fact, this one you can solve recursively to your heart's content, that these two need to be satisfied together with this equation. If I plug this in here, I can determine every next term up to any precision that I like, one by one. So this is what I did for you, and I get the following. Plus Q inverse plus 3 plus 3Q plus dot, dot, dot. And here we get minus Q to the minus 2, minus 5Q inverse, minus 8 plus dot, dot. So you can keep going and compute to any precision you like. Of course, I compute it much further because these functions now I'm going to be evaluating at taus that have CM. So at CM points, out will come some number, and I know that it's algebraic by the construction or by the CM theorem that we had on the board before. So all we need to do now is, once you've computed this to some finite precision, is to take a discriminant less than 0 and evaluate it at CM points tau of that discriminant that are also CM points that satisfy this Heegner hypothesis. So we're going to take a delta, and we're going to compute the set Q delta, which is the triples A, B, C. So I'm computing the forms rather than the roots that satisfy that B squared minus 4AC is delta. There's infinitely many of those. And I also want that the Heegner hypothesis is satisfied, namely 58 divides A. And because I want to consider things up to a sign, I won't always be in the upper half plane, I can also demand that A is greater than 0. Okay. Now that's a huge, is my microphone still on? Or okay, very good. That's a huge infinite set still. So usually, for instance, without these conditions, you would have A, B, C with a fixed discriminant. That's a huge infinite space, but there are SL2Z orbits on that are actually finite. That's what the Picard group of discriminant delta will be. With this extra condition, the same thing is true. And if I quotient out modulo this group gamma 058 plus, whatever that group is, the group by which I have to quotient out to get from H all the way down to E, then that's actually a finite set. Moreover, you can compute it using reduction theory, various tools, the details of which you can find more in the notes. Yeah, so it's a finite set of rational forms in this way. Now, to every such form, I'm going to associate S delta. I'm going to take such a form ABC, and I'm going to compute its root in the upper half plane. Yes, I'm going to solve A tau squared plus B tau plus C to give me some root. I can tell you what the root is. It's minus B plus the square root of delta divided by 2A, you all know. And that root, I'm going to plug into this power series and compute some approximation of the coordinates of that value. I'm going to compute X tau, Y tau, or at least an approximation of it, which will be a complex point on C, where of course A tau squared plus B tau plus C needs to be 0 for some ABC, one of my finitely many options, inside of Q sub delta. Okay. So in this way, I get a finite set of points on the elliptic curve. And I know that all of them secretly are algebraic. I even know over what field they're algebraic. The ring class field. Okay. All right, so let's see some examples. Yes. Sorry, this condition here? Yeah, you can omit it if you like, but then you just get every form twice with a minus sign as well. So that would give you the same point again. So yeah, so you don't win anything. If you do it in this way with the A greater than 0, the number of orbits is precisely the Picard group or the class group of O. Otherwise, it's twice the class group of O. You get every point twice. It's a minor detail. If you don't like this, you can omit it. It doesn't really matter. Okay. Okay, so this is really the point where I hesitate. Let's see. Okay, maybe very quickly, or I'll omit a little bit. It's because there's a lot of numbers, and I don't know how useful it is to write so many on the board. But I want to do at least a couple of examples. You see, this is my general setup. These are kind of absolutely determined by E, it's the modular parameterization. Now I have a choice of a discriminant that I can make. Yeah? I have my Heegner forms, but my CM point I can still choose. Yeah, so my delta is a variable still. And if I pick delta is minus 23, the imaginary quadratic field Q adjoin minus 23, or the square root of it, has class number 3. So in this case, these sets are both of size 3. I get 3 points on the elliptic curve. So then, the size of Q delta is precisely 3. And the set as delta, all of them are defined, meaning their coordinates, x and y, are all defined over Q adjoin alpha, where alpha cubed minus alpha squared plus 1 is equal to 0. So just to give you a couple of examples, the best way really to do this is not to read these numbers, but to compute them yourself. I just want to give you sort of a quick view of what this kind of thing looks like. So here's the 3 Heegner forms that represent all of the orbits. I have my 58, my 21, and my 2. And then I have 1/3 one, which is 174. 253. Don't write this down, please. 52. All of these go to some explicit approximations, which you can find in the notes. I'm not going to reproduce them for you. They're all defined over this field. They're given by some kind of big, bulky expression. But what is more pleasant to write on the board is if I add them all up. Yeah, that's what this is. That's what this trace is by the reciprocity law. If I add them all up, the result is what I've called P sub minus 23, I guess, which is on the elliptic curve over the imaginary quadratic field a priori. If I do this summation with the explicit numerical values I actually get something that's not so horrible to write down at all. I get 1, 0, which already maybe is not a point that you found. Well, it's pretty easy to spot. It's 1, 0. 1, 0 is also known as -2 times the generator P that I'd written down there. So lo and behold, this is really, when you're convinced that this is an interesting notion, what we've done here is we've constructed these points, these blue points here on the picture. We took them to be Heegner points. I had 3, just like in the picture. I mapped them over to E, I added them all up, and out comes a rational point. And that rational point is not torsion. So you see, we've won now. The CM points have won over the cusps because they were able to generate a non-torsion point. In fact, up to finite index, they generate the whole Mordell-Weil group. Okay, fantastic, right? So now what we need to know is, how are we supposed to pick delta? Does it always give something of infinite order? There's tons of questions that come up after this kind of calculation. Now, to curb our enthusiasm slightly, I also computed for you delta is -71. Delta -71 has class number 7. So now we find Q delta has 7 forms, and then we get these 7 points. They're all defined over some, what is that, haptic extension or something of the number field K. We find 7 points in this set as sub delta. And they're actually all defined over a degree 7 extension of K. And I'm not going to write them down. There's some sort of explicit, I take my forms, I map them all out. I have 7 of them this time. And if I do the same exercise and I add up all of these points, out comes 0. So 71 somehow wasn't a good choice. All of these individual points or non-trivial points over this degree 7 extension, but somehow if I add them all up, which is always a dangerous operation, 0 comes out. Yeah. It's very nice that this is a rational point. It's just not a very interesting rational point to have gone through all this trouble to construct the origin on the elliptic curve is a little bit disappointing. So clearly, this construction is very sensitive. Even if you have 2 discriminants that satisfy the Heegner hypothesis, sometimes you generate something of infinite order, and sometimes you do not. So, of course. Yes, I didn't check that, but I think that will be true. Yes. Yes. Yeah, in fact, I think it needs to be. Yeah, the secret, well, I'm going to tell you the secret in a couple minutes anyways, but there is another elliptic curve where this point is, well. Say again? Yeah, this one actually, they happen to be Q alpha. And that's connected, that miracle is connected to the fact that here, a priori, we expect something that's rational over K. We got something that was actually too good to be true. It was rational over Q. It's related. Oh, yeah. Well, I wouldn't trust these handwritten notes anyways. I would trust the typed up notes more, but even those I wouldn't trust 100%. Which is actually good that you bring it up. So the notes are, I've been updating them. They're on my website also. Undoubtedly, there's lots of errors in there. So if you see any, no matter how small, please let me know. I'd greatly appreciate it so I can fix those. So if it should be an alpha. Yeah, but in fact, yeah, don't they generate the same extension? Yeah, I think they generate the same extension. I think maybe you can do either. But anyway, yeah. It's a very nice class field, very famous for other reasons, but maybe more to do with congruences between modular forms. Okay, so the very important question that we've raised here, and in fact, it's really good to just do this computation, use a computer, but do like the first 100 or 200 discriminants and see what you get. And sometimes you get some multiple, sometimes you don't. Question? Oh, no, okay, sorry. So when are these Heegner points I've called them P sub delta non-torsion? A very important question that took a long time to answer, but finally it was answered in a very satisfactory way. Yeah, I think so, but I wasn't sure. Yeah, indeed, yeah. So they are the same. Yeah, they're the same. So you can choose either one. Thanks. Yeah. Okay. So when are the Heegner points non-trivial? Clearly, it depends on the discriminant. I mean, this is one question you can ask. You can also ask, but I don't know if I have time to ask this question. You can also ask, for every discriminant, I find some multiple of the generator. How does that multiple vary as the discriminant varies? So not just when is it 0 or when is it non-zero, but how does that multiple vary? That's also an interesting question. Oh, in other words, another way of phrasing that is, what is the sum of Bn q to the n? Well, B delta q to the delta, where minus delta is a discriminant. Where this P minus delta is the multiple of the generator that you get. Already here, I may be assuming that that's always in EQ and not just EK, but that is also true in this specific case. All right, so that's a more ambitious question you can ask. Both of these questions were answered in the work of Gross and Zagier and the work of Gross, Cohn, and Zagier, which I'll state now. Okay. So let AF be a modular abelian variety. We explored it here on an elliptic curve, but the theorem doesn't care so much about the dimension of the quotient of the Jacobian that you take. So I take A sub f associated to some new form f. And with this construction, likewise, I make my P delta in the Jacobian as a sum. So the trace I've already taken. And then I project onto the F isotypic component. That's what I have a point in this abelian variety AF, which will be defined over the imaginary quadratic field K. And it's this associated point. Then there is the following theorem. This is a theorem that's very famous and probably familiar to most of you. It's due to Gross and Zagier. It was proved, the paper came out in 1986. And it states the following amazing equality. If I take the L function of my modular form, the modular form is defined over Q, but I'm going to take the L function over K, this field that I've chosen to construct my Heegner point. I just restrict the Galois representation to K and I form the L series in the usual way. I want to know about the value at 1, but in fact, well, I want to know all of the derivatives, but Gross and Zagier tell me about the first derivative, so exactly the first derivative of this L series. And they show that this is actually the same as some constant, which depends only on the field K, so 8 pi squared over the discriminant or something, times the Peterson inner product of F with itself, times, and this is the interesting term, the canonical height inside of AF of this point, which I've called P delta sub n. That is the equality that they prove. Now, I'm not going to talk about the proof. And it breaks my heart not to talk about the proof because it's a beautiful, fantastic proof. Usually people summarize it by saying it's a direct computation. Okay, but not an easy one. Yeah, and so, but that's essentially the spirit of the proof, is you find really clever ways to find explicit expression for both sides of this equality, and then you observe that they're equal. Of course, that doesn't really do justice to the arguments in the proof, because there's some really clever things going on in this proof. And in the notes, I wrote a couple pages just giving some intuition as to how that direct calculation really goes. But in a way, it's not a lie. It's a proof by direct calculation. So in some sense, it's one of these theorems that we proved, but we still have no idea why it's true. Okay, so I'll say that, and I think that's a fair comment, but maybe it's also then fair to follow up that several of these steps since then have been strengthened. So further strengthened, meaning generalized really to other settings, notably that of Shimura curves, strengthened. And in the process of generalizing it, many of these steps were further conceptualized. By many people, but I'll mention the book of Yuan Zhangjang. There's a very general treatment of this where many of the steps become somewhat more conceptual in this calculation. Okay, all right, I'm a little low on time, so I'm going to move on to the work of Kolyvagin. And in fact, maybe it's not a disaster that I'm almost out of time, because I'm here in front of an audience that had a workshop last year and the year before that discussed in detail the theory of Kolyvagin and the descent of Kolyvagin in the context of the Euler systems or maybe more general things. But I saw that there were mini courses exactly on this topic going into the mechanics of this proof. So I'm not really going to try and add anything to that, maybe for the reason alone that probably most of the audience knows it better than me. So I'll just going to state the theorems and see what it means in our narrative that we had so far of understanding elliptic curves, torsion on elliptic curves specifically, using these rank zero quotients of the Jacobian that Maser found in its Eisenstein quotient. So I'll mention that whenever we have an elliptic curve E over Q of conductor N, and we have such an imaginary quadratic field, which satisfies the Heegner hypothesis, the next big step in this story, and it's a little bit unfair to present them so quickly after each other, because it doesn't do justice to the many developments that came in between, but nonetheless, a remarkable work of Kolyvagin proved the following. Kolyvagin proved that suppose that the P delta that's associated to this imaginary quadratic field, which would be a rational point over K, suppose that it's of infinite order. Suppose P delta is of infinite order. Oops. In EK. Then Kolyvagin does a really clever descent argument to show that in fact it must span all of the Mordell-Weil group up to torsion. So the rank must really be equal to 1, and there's nothing else in some sense behind, besides that, that Heegner point. And moreover, he also proves, all in one fell swoop, that the Tate-Shafarevich group is finite. Finite group. Okay. All right, so there's a lot to say about Kolyvagin's proof, but many of you will be already familiar given the extensive attention that it's received in recent years at this very institution. So I'll just make a couple of comments that these two theorems combined are really massively powerful statements when it comes to the Birch-Swinnerton-Dyer conjecture that we started off. And so we can kind of see that in action already here. Right? Suppose that we're in a situation where this thing is of rank 1. The Birch-Swinnerton-Dyer conjecture then predicts that the first order derivative should be related to all of these terms that we had before. Here it's similar looking, right? We have the canonical height of this Heegner point, which we suspect is a generator in this rank 1 situation. And so it really looks like a BSD type statement. In fact, if you combine both of these, you can prove the Birch-Swinnerton-Dyer conjecture when the analytic rank is at most 1. And that's really something I still wanted to do today. I would say more, but let's cut it a little bit short and point out some consequences for the BSD conjecture of these two theorems. Now, suppose that we have our situation just as before. So E over Q is an elliptic curve defined over Q with conductor N. And suppose that its analytic rank, or the order of vanishing of its L series, is at most equal to 1. So it's either 0 or 1. That's what I'm supposing. Now, I want to use this Heegner point construction, so I have to choose an auxiliary imaginary quadratic field. And I already know I want to choose it so that the Heegner hypothesis is satisfied. If you check the sign in the functional equation, you see that that guarantees it's going to be odd for the L function over K. But it doesn't guarantee that it's going to be exactly 1. So the first thing you need to do is to choose, if that's possible, an imaginary quadratic field that satisfies the Heegner hypothesis. That's certainly possible. That's a congruence condition. So there's infinitely many such discriminants that we can take. But in addition to that, I also want it to be true that the analytic rank of the L function of E over K is exactly equal to 1, not 3 or 5 or anything else. It has to be exactly equal to 1, which is what you expect generically, really, but it requires some proof that you can always do that. And that's a fairly soft analytic argument. It's not easy, but it pales in comparison with the theorems that we're going to apply. Now, combining these two theorems on the left boards unleashes their full power together in the following sense. By Gross-Zagier and Kolyvagin, we know that this P delta, first of all, by Gross-Zagier, it's not a torsion point because the analytic rank is precisely 1. So this L value here on the left, in other words, is non-zero. And the previous one was 0. That's how we chose our case, so that this thing is non-zero. That means the right-hand side had better be non-zero as well. In particular, this canonical height of the Heegner point needs to be non-zero, and that can only happen if it's a non-torsion point. Canonical height picks up precisely when a point is torsion or not. That's exactly where it vanishes. It's not torsion. Now, if you know it's not torsion, now we can apply Kolyvagin. It's a ping-pong kind of arguments. They are in dialogue with each other, and they say, well, now it's of infinite order, so now I know that actually the algebraic rank over K is exactly equal to 1. Yeah? So by Kolyvagin, the algebraic rank over K, right, is precisely equal to 1, and it's generated, therefore, up to finite index by this P delta. Okay, now, it's somewhere inside of this module, but of course, we have an elliptic curve over Q. We want to prove a result over Q, not over this auxiliary choice of K that we picked. So we're going to observe that, in fact, the space where it's a member of, if I tensor it up to Q, well, it's the same as the part of the Mordell Weil group. We're going to decompose it, where complex conjugation acts trivially, and then the part of the Mordell Weil group, tensor Q to avoid torsion issues, where complex conjugation acts by -1. You can decompose it in this way by just projecting along the eigenlines for complex conjugation. Now, if I look at this, everything that's fixed by complex conjugation is actually just a rational point. Yeah? So this group here, that's literally just the group that we're interested in, these tensor Q. Whereas the other guy, that's exactly the rational points on the quadratic twist by the discriminant delta. Yeah? Because those are the points that are sort of purely imaginary. They always have this coordinate that's a multiple of the square root of d. So if you translate, if you pick the square root of d and you put it into the equation, it gives you an actual rational point on the quadratic twist of E and of, again, tensor Q. Okay? So we have our Heegner point here, this P delta, it generates this. All we need to figure out is what complex conjugation does to it. Does it land inside this factor or this factor? That's what we need to know. One of the two, right? Okay. Now, luckily, we understand exactly how the Galois group acts on Heegner points. Yeah, that's part of Shimura reciprocity. Here we're acting by a special element. It's the Galois group of K over Q. It's the complex conjugation. It's the second line in the Shimura reciprocity law that I stated. And it tells us precisely how we're supposed to take this projection. So to determine the projection of this P sub delta, we note that the following implications are true. You see, if the analytic order of E over Q this time, yeah, is equal to 0, well, then we know the sign in the functional equation. The sign in the functional equation must be even, because it vanishes to even order. Sorry, am I saying that right? It must be odd. Yeah. And so this means the sign is completely determined by the Atkin-Lehner involution. So we know that this P sub delta, by Shimura reciprocity, it's the same as the Atkin-Lehner or Fricke involution of this P delta. But I know what that does to the Heegner point because I know precisely what the sign in the functional equation is by this assumption. That must be precisely equal to minus P delta. So that means that my Heegner point lands in the wrong part. It's a rational point on the wrong elliptic curve. This guy doesn't receive this Heegner point. And because the Heegner point generated the whole Mordell-Weil group over K, we know that there's nothing left for the Mordell-Weil group over Q. And we conclude that also the algebraic rank must be equal to 0. And the argument is precisely the same when the analytic rank over Q this time is equal to 1. Except the sign in the functional equation now is different. And so P delta is fixed by complex conjugation. It gives you a rational point. And since the rank over K was exactly equal to 1, also the rank over Q is at least 1, and therefore at most 1. It's precisely. Okay, so we get these wonderful implications that the analytic rank implies that when it's less than or equal to 1, that the algebraic rank is the same. That's really tremendous progress towards the Birch's-Swinnerton Dyer conjecture, especially given that we expect 50% of the elliptic curves when picked at random to be rank 0 and 50% to be rank 1. So that's pretty good progress. Okay, I will just mention that I presented everything for elliptic curves, but it's very useful to know that it's just the same argument essentially works without any change, the same argument that proves this theorem, which I didn't go into. It proves that also for modular abelian varieties. So you can find this in a paper of Kolyvagin and Logachev, and they generalize this to abelian varieties over Q that are modular and they prove, and this will be very useful for us in the next 5 minutes, that as soon as the L value is non-zero, so the analytic rank is equal to 0, then in fact it is still true that the Mordell-Weil group is finite. Okay, very useful to know also in the Chaboty context, if you're trying to show that you have a certain rank 0 quotient, you can check it analytically, which is a finite computation. You just have to check that the L value is non-zero. So all you need is one, well, the right digit of precision to show that the L value is different from 0. You can do that numerically. All right, and so just to finish, is that by the same remark that I just said, is that on modular curves, it's now become a lot easier to construct rank 0 quotients of the Jacobian. All you need is to find a modular form whose L value is non-vanishing. You can apply lots of analytic techniques to show that such a modular form exists and that they exist in abundance, etc. And that is precisely what happened, and that's where I want to end on, in the work of Mirel on the winding quotient. So instead of Mazur's Eisenstein quotient, which I didn't really define for you, maybe in words, but not really exactly, you could have taken a different one, which is also quite easy to define. You can find in the modular Jacobian J naught of n the so-called winding quotient, which is defined as follows. The abelian variety A, which is obtained as a quotient of J0 of n by the image of some ideal, the winding ideal, where that winding ideal is the annihilator in the Hecke algebra of the winding element. And I have to tell you what the winding element is, where this C wind, it's the element of H1 x0 of n, so singular cohomology with rational coefficients, that corresponds to the divisor supported at cusps, that is the difference between 0 and infinity. Okay, or infinity, 0 is the same. So this element, it's something in the relative homology a priori, but it defines an element of the dual of the space of holomorphic modular forms. And we proved already that was the content of the statement of Manin and Drinfeld, but that's actually contained in H1 with rational coefficients. Now, H1 with rational coefficients has an action of the Hecke algebra. And I take the element corresponding to this particular divisor in here, and I take out everything that kills it. And now I take the quotient by the image of that ideal. Now, this winding quotient has the wonderful property that, in fact, any isogeny factor that you can find associated to a new form F satisfies, by definition, that if I take the L value at 1, the L value at 1 we saw in the very first lecture up to some explicit constant, which I think is just 2 pi or something, but let me omit it, is just the integral from 0 to infinity of fit t to the s dt over t. This we saw, this was the integral representation of the L function that we used in the very first lecture, both to do explicit computations and to get the analytic continuation and the functional equation. Now, this time we see by definition of this L function and expressing it in this way, what we're computing here is literally the pairing of this element, viewing it as an element of the dual space of the holomorphic modular form. And so because we've quotiented out by the kernel, we know that this is non-zero. So every F that you find in this quotient has its L value non-zero. So now I can use Kolyvagin and conclude that actually the rank of that piece is also zero. Very easy. I didn't have to do any work. I just wrote down this definition and I immediately found that the rank was equal to 0 without any descent required. Now, that's of course an outrageous thing to say because it relies on Kolyvagin's descent. It's a very difficult descent, but if we take that as a black box like we have been doing today, that is pretty cheap. Now, on Mazur's list of properties that we were looking for was something else beside having ranks. We needed to find a quotient of the Jacobian J naught of n that had rank 0, and also that was a formal immersion at infinity. And that second one, that's not so obvious. That's something that needs to be checked. And that's what Loïc Mirel did, a paper that appeared in 1996. And he showed that indeed this winding quotient does satisfy that. And because of that property, and this winding quotient has a definition that's technically simpler, that was the key innovation for him to generalize the arguments of Maser to other number fields. He proved the following spectacular result using this conclusion, that whenever E over K is an elliptic curve, and don't confuse this K with the K that's been floating around throughout this lecture, K here is any number field at all. The quadratic case had already been appeared in Kamieni and Maser, but for any number field at all, Mirel proves the following. There's an analog of Maser's theorem, which is both better and worse. It says that if I take the torsion group, there's only finitely many possibilities for the structure of it. And he proves that by showing that, in fact, the order of this torsion group over K is bounded by some explicit bound. He doesn't make the full list, which that seems very difficult to do for a general number field. But to compensate for that, there's this amazing feature that this bound only depends on the degree of the number field K over Q. So the bound doesn't change if you change the quadratic field, for instance, or the cubic field or whatever. All right, so that was really the key technical innovation, I think, in the work of Mirel, is to switch from the Eisenstein quotient to the winding quotient. And now, at the end of all of this, we can understand a little bit better why that was and what the definition of that is and what that relied on, replacing, in effect, Maser's descent with Kolyvagin's. Okay, so in the context of this conference, my time is up, so I'm going to stop. But in the context of this conference, many of the things I've talked about, they were, of course, pure kind of number theory, and they were just about the arithmetic of modular curves. But I've tried to emphasize things that can be useful in the explicit determination of rational points using techniques like classical or quadratic Chaboutier. And so in particular, these analytic techniques here are very, very useful. And in fact, they've already been used in some of the other lectures. Yesterday, I think Jennifer already used these kind of analytic methods to show that some of the examples that she was treating did have rank 0 or did have rank 1 or etc. So those kinds of statements are typically verified using these pieces of partial progress towards the Birchens-Minot and Dye conjecture, which in practice are very powerful. So with that said, I'm sorry for going slightly over time, and thanks very much for your attention for being here.
Questions? Okay. If not, let's thank our speaker again for a lovely lecture.
Yeah, on behalf of the organizers, I thank you for your wonderful and excellent lectures, and also thanks for interacting with the
Thanks for
participants.
having me. It's really been a lot of fun.